right. Well, good afternoon and welcome everyone. Welcome everyone here in person in 10250. We're sorry the room is not quite big enough for everyone, but it's great to see everyone here in person. It's also great to welcome everyone who's joining us online, friends and alumni around the world. My name is Troy Van Voris. I am the department head of the Department of Chemistry, and it's my pleasure to welcome you all to this celebration of the work and discoveries of Professor Moungi Bawendi, the co-recipient of the Nobel Prize in Chemistry, along with Lou Bruce and Alexei Ekimov for their work on techniques to generate quantum dots of uniform size and color. Now, Moungi started his academic career down the street at Harvard, where, fun fact, he failed his first chemistry exam. So all of you who are currently struggling in 511-1, take heart. There is a future for you. He earned his PhD from the University of Chicago and continued doing a postdoc with co-honoree Lou Bruce at Bell Labs. And he joined the MIT faculty in 1990 and has been a fixture of the MIT community since then. Now, to me, the most fascinating revelation of chemistry is that it shows us that atoms and molecules do not obey the rules that we are used to in our daily lives. They obey a different set of rules. At the nanoscale, we find that atoms can actually be in multiple places at the same time. We find that molecules cannot adopt just any energy. We find that there are physical fundamental limits on our ability to visualize and probe things on the nanoscale, molecular scale. And Moungi's work fundamentally reveals that this fascinating nanoscale world of chemistry impacts the tangible real world in important ways, leading to brighter displays and novel forms of biological imaging. Now, this is the part of the introduction where I would normally list off the honorees' many, many accomplishments. But stop me if you've heard this before, but Moungi won the Nobel Prize. And so without further ado, please join me in welcoming the MIT's 2023 laureate in chemistry, Moungi Bawendi.
Well, thank you, Troy. That was a really nice introduction. And I love the idea about atoms being in two places at once. I live for that kind of stuff, with quantum mechanics. It's wonderful. So it's great to be here to give this talk amongst friends and for all the people online as well. I know my stepmother is listening to this. So you can see that my talk title has undergone a number of changes. This was the original title from Stockholm, and then I think the pamphlet has a different title, and this is a slightly different title, but it's all about the same thing. It's about creating a synthesis that we really had to create in order to be able to, for me to have a career at MIT. And that synthesis basically opened up a world that we didn't expect 30 years ago. So let me start. There's still some people that don't know what a quantum dot is, probably even at MIT, certainly online. So let me start from the beginning. What is a quantum dot? So a quantum dot is a nanometer-sized piece of a semiconductor. It has between hundreds to thousands, maybe 10,000s of atoms. It doesn't have to be silicon. This is a binary semiconductor made of two different kinds of atoms. You can have semiconductors that are not silicon. And when you image them using an electron microscope, you find that in this case here, if you make them right, they're basically all the same size. In this case here, they're probably about 5 nanometers on the size. What makes them special is if you put an electron in a quantum dot, it shows quantum size effects. The quantum world shows up in these particles, and that's the beauty of them. That's why they're interested. So when you think of an electron in a semiconductor or in a wire, you think of it as a particle moving around the wire or the semiconductor. That's the macroscopic world. But if you try to put that electron in a box, a nano box, like the 5 nanometer boxes that we were making, it no longer acts like a particle, it acts like a wave. That's the particle-wave duality of matter when you get to the quantum regime. And our nano box is the quantum dot. So because it's a wave, it obeys the same sort of things that you already know, for instance, for sound waves, that the size of the cavity has a big impact on the pitch for a sound wave. So it's going to be the same thing for electrons or for light when we get to the emission of light. So for instance, we know that a small wave emits a high-pitched sound, like a piccolo would compare to a flute, which is a lower-pitched sound. You see it in organ pipes, where the small organ pipes have a higher-pitched tone than the large organ pipes. You hear the fundamental, but there are also a bunch of harmonics that get emitted from that. So it's not just the lowest, longest wave that exists in there, but it's also all sorts of waves that have shorter wavelengths. You hear the fundamental more strongly, but if you have a great violin, it has a rich sound. The sound is because the fundamental is along with all sorts of harmonics. Those harmonics are also present then in the electrons that we put as waves in the quantum boxes. How do we put an electron in a quantum box? There are already a whole bunch of electrons in there because this is made up of atoms, but they're tightly bound to the atoms. So we've got to sort of loosen up one of the electrons and let it fill the box. One of the ways we can do that is by shining light. By shining light, we sort of take one of those electrons from one of the atoms in there, it gets excited, fills the box into one of these waves. Now, with a wave of the electron depends on the size of the cavity, small particles, smaller cavities. For electrons, the size of the wave is related to the energy. So a small wave corresponds to higher energy, and large wave corresponds to smaller energy. That electron eventually comes back. That's the fundamental here, right? So you're exciting the fundamental, what I'm showing here. You can also excite the harmonics, and I'll talk more about that in a little bit. Eventually, that electron finds where it came from and loses its energy and emits that energy as a photon, as light. And so we see that then in fluorescence as light being emitted from the different size particles. Okay, so that's the basics that you need to know for what a quantum dot is. Now let me tell you how we got here. So I was in Stockholm on December 10, getting my prize, this medal here, along with Lou Bruce and Alexei Ekimov. And the citation is for the discovery and synthesis of quantum dots. Now, the discovery was by Lou Bruce and Ekimov. Lou Bruce was working at Bell Labs in the US in the early 1980s, and Alexei was working in the Soviet Union at the time, behind the Iron Curtain, late 70s, early 80s. And they came up with this discovery of the quantum size effect in these particles around exactly the same time, within a year of each other, basically. Alexei was interested in color glasses. What gives the beautiful colors that you see in some stained glasses or other kinds of color glasses that are made from adding metals or combination of atoms to the glass and melting it and let it cool down. And depending on how you do that, you get different colors. And so he started investigating that, and he was working in an environment where the idea of quantum confinement was there, because this was the time when physicists were beginning to really think about quantum wells, which is also a sort of a kind of quantum confinement, but in a plane. And he realized that even though it was always the same atoms that he was putting in there, depending on how he processed the glass, he would get different colors. And he described in his first papers how this change in color with processing was due to quantum effects in the small particles. And he used small-angle X-ray scattering to find out what the size of these particles were. These particles are embedded in glass, and eventually, they're not very useful if you want to process them and make things out of them, but they're very good for beginning to understand the basic physics. Lou Bruce was working at Bell Labs in the late 70s during a time of an energy crisis, looking at the possibility of using semiconductors and light, or sunlight in this case, to do photocatalysis and generate hydrogen. It's an old story that we're still talking about today. And in order to capture the motion of that electron from the semiconductor to the liquid, he decided to make the semiconductor smaller and smaller and smaller to increase his surface to volume ratio to get better signal to noise. He was working with cadmium sulfide as a semiconductor, and he realized, or he didn't realize, he observed that depending on how he processed, how he tried to make his cadmium sulfide, he was making this in water, not at high temperature like Alexei, in water by adding cadmium salts and hydrogen sulfide, in this case here, bubbling it through the solution, that the color also changed. It wasn't always the same. Sometimes it was a longer wavelength, sometimes it was shorter wavelength. And he was surrounded, again, at Bell Labs by physicists who were interested in quantum confinement. And so he realized, in this case here, using electron microscopy to see the size of the particle, he realized that what he was looking at was the quantum effect in these. Now, this quantum effect had been predicted many years before, but this was really the discovery that it actually existed. My part of it was the synthesis, which was my first paper out of MIT in 1993, and that was the Nobel Committee acknowledges that's the paper they gave me the prize for. And that's what I'm going to tell you where that came from. Okay, so I was a postdoc at Bell Labs. I had been a theorist and a high-resolution infrared spectroscopist, gas phase spectroscopist, looking at small molecules of interest in the interstellar space. For instance, H3+, 3 protons, 2 electrons. You know, how simpler can you get it for a polyatomic molecule? That was my background. So I come to Bell Labs as a summer student in 1988 during my graduate school, and I see this incredible world that I didn't know existed of condensed matter physics and solid-state chemistry and everything that was going on there. That was just amazing to me. So I go back as a postdoc, and my first assignment as a postdoc with Louis is that Louis and Mike Steigerwald and Paul Vasados, who had been postdoc right before me, had found that if they took the particles that they were making at the time in pyridine, which is a kind of what we call today a Lewis base, and cook it up, boil it, that the absorption always looked the same. And it was very sharp. It was more like a molecular absorption. And they thought maybe what was happening is that what they were creating was we called a charge transfer species, where there was an electron that was going from the quantum dot to the pyridine on the surface. And maybe that was the case. So that was my first assignment. So I was a theorist, so we said Lewis base. I asked Mike Steigerwald, what's a Lewis base? And then he showed me in his lab, okay, there are phosphines, pyridines, amines, all these beautiful molecules that are Lewis bases. And so I found all the Lewis bases that I could find in his lab, and I made small particles using the water-based synthesis at room temperature that they were making. I made small particles, and I started cooking them in these Lewis bases, trying to see if I could reproduce this, interesting observation with pyridine. Pretty much nothing interesting happened except for one bottle of tributyrophosphine, which is a Lewis base that has a phosphine there, phosphorus atom. And then I cooked in, and I saw growth of the color from yellow to red, and the particles starting to emit light. Before that, we never saw light coming from the particles. They absorbed light, but they didn't emit. And wow, that was amazing, but. And I called that the phosphine prep. And I've got a couple transparencies from that time period, from 1990, after that observation, that describes the initial preparation that Mike Steigerwald and Oliver Sados and Bruce had come up with, the inverse micelle prep, basically growing little particles in water, This is a little bubble of water surrounded by soap molecules in hexanes, pentanes and hexanes. So you add a little bit of cadmium, and because it's a little bubble of water, it's maybe tens of nanometers in size, this little bubble of water. You have a few atoms of cadmium. Then you add a selenium precursor. This is bis trimethylcytoselenide that reacts with the cadmium, and you form this very defective, very ugly sort of particle, misshapen, just like it is in my transparency here. And Steigerwald's genius was that, well, this is still an active surface, so we can follow that up with a phenylselenide coating. And with the phenyl groups now on the surface, this is no longer water-soluble, water-dispersible. So it comes out of the bubble and it's not particularly dispersible in the hexane either. So it falls out as a powder out of solution. That was a really great discovery, this particular synthesis. Then they realized, well, this crystal structure is really terrible. Room temperature, you're not going to form a good crystal. So they decided to anneal these things to increase the crystallinity. And that's where they used the pyridines, in this case at 160 degrees. So the phosphine that I used, I call that the phosphine prep, was to take what came out of this little powder and redisperse it in these butyl phosphine, tributyl phosphine oxide, increase temperature to 230 degrees. You'll see temperature is important here. Reflux for about 300 hours, and slowly you take really tiny particles here as seeds. So this is the idea of nucleation and growth that is well known in physical chemistry from the 1950s. So you have a seed crystal here, and you slowly grow it out. And the color turns red because the wavelength of that electron gets longer, the energy is lower, so it looks redder. And you get this particle surrounded by these phosphine oxides that are stable pretty much indefinitely in solution. And I called it magic. I called it magic, which is not a scientific description, because it didn't always work. It worked some of the time. And the crystal structure was like that you'd expect from a piece of the bulk. So we had annealed all the defects. And so we wrote a paper. Where we were very honest, occasionally it worked, right? The point of the paper wasn't the synthesis. In fact, in the early years, the synthesis usually was a footnote. The point of the paper was that we could make that little pieces of the bulk that looked like the bulk with a crystal structure that was like the bulk. And this is a spectrum. This is the absorption of the light. So this is the light frequency of light here. So this is red light on 700 nanometers. This is UV light here. At room temperature, these little defective particles, they look like white noise, in a sense. There's no fundamental here. There's no clearly visible harmonics in the absorption. Just maybe here, there's a fundamental here, right? You start to anneal it, you make the crystal structure a little bit better. There's a fundamental that starts appearing here, maybe a harmonic here, but a lot of noise here. With the phosphine prep at a higher temperature, that harmonic is better defined. We call that the exciton. That's creating that electron, freeing it up to fill up the box. Okay, that was good, and I did a lot of experiments in my postdoc with that. Better crystallinity, tighter distribution. The crystallinity here, this is an X-ray, powder X-ray. The width of these peaks is inversely proportional to the crystallinity. So as they get narrower, that means better crystallinity. These 3 peaks means that this is really the bulk that you're looking at here. So this is all great. But I could only make one size every now and then. Okay, so that was me at Bell Labs. So now I come to MIT and I have this proposal to do all this physics and all this stuff like this. And I'm praying that I'm going to be able to do this more than once. So I come to MIT and I set up my lab, and I've got 3 brand new students, eager to go. And we start making particles, and the occasionally becomes never. Okay, so this is a bit of a problem. In my memory, when I talked to Chris Murray, my first student, I thought that this never lasted years. He reminded me the never actually lasted just a few months, because we quickly realized we were spinning our wheels. We had to just change things completely. Okay, realizing that what we had done back at Bell Labs, what I had done with Lewis, was basically a nucleation and growth sort of process, and that water was terrible for these materials, that we should just get rid of the water completely. It was an extra step that we really didn't need, and go to pure air-free organometallic chemistry. And Steigerwald had taught me everything that I know about inorganic organometallic chemistry, so I took that knowledge and came to MIT and applied it with my students, and we created what is now called the hot injection organometallic air-free synthesis for these quantum dots. This is the synthesis that ended up being the Nobel Prize synthesis, and which is being used widely today all over the world, even in manufacturing situations, because it's highly scalable. Okay, so what was that? So it was very simple. You put a solvent with some coordinating ligands. You have your organometallic precursors. You heat this up to whatever the temperature is for that solvent and their ligands. You quickly inject your precursors. That forms little seeds. That's your nucleation. Once you nucleate, then your concentration is not high enough anymore. You used up material. Nucleation stops. And the only thing you can do now is grow on top of the existing particles. That's the growth phase, and that can take a couple hours. And that slow growth then allows you to stop the reaction at any time simply by cooling the solvent and getting a very tight size distribution. Okay, so that happened in December of 1990, actually, right here at 220 degrees. But it was still the case that we couldn't make big particles. It was mostly just one size. And the tributyl phosphine that we were getting was very expensive and came in these little tiny bottles. And my startup money was quickly being used up. So we had to switch things around. We wanted to have a higher temperature. You know, my goal coming to MIT was nearly defect-free quantum dots, a size series, consistent surface chemistry, narrow. So we had the consistent surface chemistry and the narrow size distribution after this, but we didn't really have a size series in order to study the physics from atomic to bulk. You want a size series. So we realized that by taking longer alkyl chains on that phosphine, we could go to higher boiling points. And it turned out that the trioctylphosphine oxide is used in the mining of uranium. So it doesn't come in little bottles. It comes in train car full of this stuff. So it's very cheap. So that was great. So we switched to that. And now I have a laser printer because it's 1992 now. So crystallinity is great. Uniform surface is great. Monodispersity from the nucleation and growth. Organometallic precursors, no water. And slow growth, we can extract with methanol and redisperse in all sorts of solvents and begin to process them like if they were very large molecules. Okay, this is a video from 2009, I think. So this is when YouTube first came out on the market, and the students were really eager to do videos of all sorts of things. So there's the injection, the nucleation. Okay, these are the seeds. This is at 300 degrees Celsius. And then it's slowly growing. Here the student is taking some aliquots out, and we'll see the size series. And I'll spare you the 30 minutes of growth. And here it is. It's now bigger, so the color is darker. And he's still taking aliquots of growth out. And now you can see the colors changing. So the color is because the energy of that electron gets lower and lower as the size gets bigger. And there's a size series here. So now we have a true size series. We can begin to study the physics. And then they emit light, and this is the fundamental now that you see with your eyes, the fundamental of that electron there, releasing an energy as different colors of light of different energies. So this is the paper that we wrote in '93, my first paper at MIT. And I underlined a few things. It was simple. I was a physical chemist. I was a theorist. It had to be simple. Consistent crystal structure, monodisperse, very tight size distribution, a single reaction. That turned out to be really important because it was very portable and it could be scaled up for manufacturing. We were still chemists, so we knew we had to purify things. So when you make a new molecule, you have to purify it, right? You do whatever you need to do. So Chris Murray invented a precipitation, which we call size-selective precipitation. By slowly titrating a non-solvent, we could get the biggest particles out first, get rid of the biggest particles, keep the whatever there, do it again, and get rid of the solvent. And now our precipitate is a really narrow size distribution, purified. All the precursors are gone. It's a pure precipitate of quantum dots. You can see they're basically all the same size from that paper. The dotted line is the crystal X-ray, powder X-ray. The solid line is a model of what an X-sized piece of the bulk would look like if you just take it out. And the line width corresponds to the size of the particle. So it's a true piece of the bulk with very few defects. Now we can see the harmonics in the absorption. So there's the fundamental, and these are the waves that have more waves than one cycle, basically, of the electron in the box. And the emission is nice and fairly bright. So I said at the time, it's pretty bright. It's got a quantum yield of 20%. It means that for every 100 photons get absorbed by the particle, 20 of them are emitted as a different color light. And one of my colleagues in Germany said, yeah, 20%, that means that 80% of your particles are trash, but he used a stronger word than that. Okay, so, all right, so maybe I'm a little too optimistic here. But anyway, it was better than 0, which is what it was when I was at Bell Labs, right? So we were on our way to actually do physics because that's what we were really interested in. We needed the samples to do the physics. Okay, this is from Chris's thesis, and you can see here, this is now color here as a function. So he's taking little aliquots out as the particles are growing, and the difference between every spectrum here, every sample, is probably no more than maybe a dozen or 20 atoms. So he's got exquisite control over the size as he comes out. And then you can see this harmonic sort of changing around, and that was my interest as a physical chemist. What are they doing, these harmonics? And so David Norris, who was waiting patiently to do his experiments in low temperature experiments, looking at the spectroscopy of these are the room temperature spectra here, from small particle to large particles. And looking at these harmonics, the separation and entry of these harmonics. So these are large particles on that size, small on that size, and you see the fanning out of all these harmonics. And there's a thing that you see here, that this harmonic wants to go up, but it's repelled by this one here. That's called an avoided crossing. And as a spectroscopist, when we see avoided crossings, we go, oh, our heart skips a beat because these are telling us something really fundamental about how these electrons are interacting with the atoms that make up the box. Okay, so we're beginning to learn about the actual physics of happening in these particles. Theory had also predicted that there would be a strong dependence on the magnetic field of certain properties. For instance, here, the lifetime of the emission. There's Minoj, my first student with, we called it the space shuttle because filling it with liquid helium basically filled a room with water vapor. And you can see then, we observed then as a function of field, there was a change in lifetime. So this synthesis was simple, but it really gave us really good material where we could really begin to understand how those electrons that we were putting in the box interacted with the atoms, because the box is not empty, and how that changes the function of size. Because the interest really was, you've got atoms that have very interesting properties. You've got bulk material that also has very interesting properties, but they're not at all like each other. An atom doesn't look at all like a piece of bulk, right? And so somewhere in between, there's this transition from atomic-like to bulk-like. And that was really the fundamental question that we were trying to answer. how does that transition look like? You have different properties. You've got the electronic properties. You've got the vibrational properties. How do all these properties evolve from the atomic to create what we know as the bulk? And so this was our way to, this allowed us to begin to understand this. And so this is science that is still going on today all over the world. Because these particles were all the same size and looked all the same, it turns out that they also crystallized. They created what we would call a supercrystal. And we saw that very early on, published this. And these supercrystals could be actually quite large. And so this is an optical microscope, a light microscope image. This is an electron microscope, SEM's image of these. And this is Sherry Kagan, who did these experiments, also one of my first students. And so now what we're starting to make here are crystals of what we might call artificial atoms, where we have one electron in there that's atomic-like in its behavior, and then we have a bunch of this, but now on a much bigger scale. This is a field that has, Chris Murray brought it with him to Penn, and still working with Sherry, who's also at Penn. And now the field has realized that you can make all sorts of material with this process. Not just cat selenide, not just semiconductors, but also metals, oxides, magnetic materials. And you can start to mix and match all these materials together to form new kinds of crystals, where the building blocks are no longer atoms, but are these particles, looking for new properties that could be tuned by the interaction between these new. So basically creating a new periodic table, not an atomic periodic table, but a nanoparticle periodic table. An important step was also to realize, and this is something that Mike Steigerwald and Lou Bruce had realized early with their own synthesis, is that that surface was still chemically active. So you could grow on top of it, and you could grow a shell of a different material. And so realizing that this quantum yield issue, this 20%, which seemed pretty bright to us, wasn't 100%, which is really what we wanted, was because the surface was right there, and there were defects on the surface, and that allowed us to lose the energy of that electron through interaction with the surface. So if we could build a shell that was a really nice shell that could contain that electron in the middle without it seeing the environment, that could be a way. So there were a number of groups, including myself. Philippe Guillaume at Chicago was the first to break the 50% quantum yield here. Today, the same scheme of a core shell allows us to make particles that have 100% quantum yield. So they're no longer trash, right? Right, and that's what's in the TVs. The Samsung TVs have particles that have 100% quantum yield that gives them their green and red color to the TV. And so now you can have a psi series, or changing the material, because cat selenide isn't the only material. The TVs have indium phosphide in them, for instance. By changing the material and the size. Okay, so I think that's Siri talking to me. And then you realize, okay, so this is interesting, because this is the absorption here, and the absorption absorbs any color to the blue of where it emits, which means that you can have all of these different materials and excite them all with the same blue light. Okay? This is great, because now you can think about using these things for multiplexing. You have a bunch of particles, they're attached to different things, and you use one blue light. This was one gallium nitride diodes were also coming out in the late 1990s. And so combined with that new technology, that became the impetus for a lot of inventions in that field. The ligands that we used to make the balls, we used one kind of ligand, the phosphine oxides. But if you mix and match and use multiple different kinds of ligands that have different interactions with the different crystal fields, people realized in the early 2000s now, about 7 years after the synthesis, that you could start to grow different shapes. So Paul Vasados and his group made rods, Dubertré in France made platelets. These are our contributions. These are cat selenide rods with little bells of cat telluride where the electron goes, you create it in here and then it goes to the edges. These are nanoplates of cesium lead halide perovskites, very, very thin, made recently in my group, for instance. So not only do we have different materials, we also have different shapes, and now the universe that's available to us to mix and match becomes really infinite. And that's a little scary, but if you're clever, then you can figure out how to mix and match things to try to make new materials. This idea of assemblage also isn't confined to making big crystals of particles. Now we have two different kinds of dots here. These are the cat selenide quantum dots. These are magnetic particles. These are iron oxide particles, which are made using a very similar process, also all the same size. And it turns out if you mix these two together in certain ways, you can make super nanoparticles. These are about 100 nanometers or less, a little less in diameter. They're both fluorescent and magnetic at the same time because they contain both of these particles together. They react to a magnet. They react to UV light. It turns out that the quantum dots are on the outside of these large balls and the magnetic particles on the inside. We were doing biology experiments with quantum dots at the time, so we decided to see if we could use this as a dual sort of imaging agent. So this is a mouse model. This is a GFP, so green fluorescence protein mouse model. So this is the GFP imaging here. We inject these particles, and this is a carcinoma in mammary carcinoma in this model, and you can see then the particles basically get trapped inside the tumor here through this enhanced permeation effect. And at the same time, you can read it in the MRI, the increase of the concentration of these particles because of the magnetic properties. Okay, more science. They were really bright. Single molecule spectroscopy was beginning to be used in the 1990s. W. Murner, Nobel Prize in Chemistry a few years ago, pioneering some of these things. And so I thought, okay, so we can see single molecules. We can certainly see this. And because even though they're all roughly the same size, every particle is still different. There may be one extra atom here, one fewer atom there. So if we really want to study the physics, we got to study them one at a time. There's really no other way. The ensemble really messes up things. And so we started doing that, and what we find is that they're really not that stable. There's interesting things going on. So you could say, okay, this is trash, or you could say, wow, there's interesting physics going on here, right? So they blink on and off, and when you go to low temperature, at liquid helium temperature at 10 Kelvin, then suddenly you can see that this absorption, this fundamental absorption suddenly gets really narrow in energy, and then you can start to see what we call phonons, which are basically vibrations of the particle. So you can begin to understand how that electron is coupling to the motions of the atom and how strongly that coupling is happening. So this was 1996, and we're still doing single quantum dot spectroscopy today. So these are movies. This is the ensemble fluorescence. Okay, it's completely stable because there's a gazillion particles are emitting at the same time. If you look at room temperature, you see that it flickers, it does all sorts of things. At low temperature, it's narrower, but it also moves around. These are little sensors of the environment. Okay, so you can make lemonade out of these lemons and use them as sensors of the environment, and you can learn some physics out of that, of this dynamic spectrum. For instance, if you take the spectrum energy here as a function of time at low temperature, you find that the spectrum, this energy of that electron emitting a photon, the energy jumps around, okay? And we understand what that is. It's because the particles every now and then charge up, so now they have an extra electron in them, and then neutralize, charge up, neutralize. The surface has charges on it, and those charges move around. That creates an electric field, a Stark effect. And so these little motions here are due to the Stark effect of the environment. So we're basically having a sensor of the environment. So we're looking at the local charge dynamics and the charging of the particles. More recently, this is now going 25 years ahead, by looking at individual photons from, in this case here, cubes of cesium lead halide perovskite particles, we're finding that they can emit what we call indistinguishable photons. And these indistinguishable photons, in the presence of a beam splitter, can coalesce together. This was the topic of a Nobel Prize a few years ago in physics, I think actually last year, 2022. This experiment here for the cognoscentes tells you about if they're indistinguishable, the central peak here should go to 0. If they're not, if they're distinguishable, then it goes to 100%. And the fraction here tells you how many pairs of photons that you're measuring are actually identical to each other. So we have a visibility of what we call visibility of 50%, which without doing anything special is actually pretty good. There's a lot that can be done now to make this go from 50% to 0. Okay, application. So the synthesis happened in 93. People started making core shells in 96. And very quickly, the idea that you have this bright emitter that can absorb any blue light, independent of the size, etc. The first application that people thought about was in biomedical imaging. And there was a corporation that came out of that company, Quantum Dot Corporation, that came out of the spin-off at MIT and Berkeley. Founded this with Paul Vasados and Shimon Weiss. And this is a slide that actually came from a paper from the company where they labeled the nucleus of this cell with quantum dots and the outside with a dye from what was then molecular probes. And I think molecular probes hated this slide so much that they ended up buying the company to get rid of it. Because it shows the dye sort of fading away and the quantum dots being really solid and not interacting, not degrading with the light. We worked hard on surface chemistry to make these compatible with the in vivo environment. This is an injection of quantum dots in the mouse again. You can see the quantum dots sort of diffusing out of the vasculature without aggregating. We worked hard on how to conjugate the quantum dots to the outside of the cells using bioorthogonal chemistry. This is an in vivo experiment here with the Jane group where we labeled 2 color dots to label these very rare cells in the bone marrow. And so we start with the red dots and then the green dots, and only these very rare cells have the 2 receptors on them and the absence of a blue stained nucleus. And so when now you look in your microscope, you're looking for yellow because green and red make yellow. And there's that one cell here, this hematopoietic precursor cell. And then you can start to study its environment and study how it behaves. Kind of a hero experiment. More applications in downshifting. So these biology applications are examples of downshifting light. You take blue light, you shift the color from green to red or whatever. You don't have to do that just in biology. There's other things that are easier to do than biology where this is important. 2 companies came out with this idea, NanoSys in 2002, QD Vision in 2005. QD Vision started by 2 MIT students, one from my group, one from Vladimir Bulovich's group. NanoSys was an aggregate of IP from many universities, including MIT. They've both been bought by other bigger companies. The first product that came out from QD Vision actually was, at the time, these LEDs that were starting to come out to replace fluorescent light bulbs or incandescent light bulbs were a little too blue. They were so blue, in fact, that you really didn't want them in your bathroom, because if you looked at yourself in your bathroom, you looked terrible, right? There was no red in them to reflect the blood from your skin. And they were also very expensive. So the first idea was, okay, so let's warm up the color by taking some of that extra blue and downshifting it to red to create more red, to get that color temperature a little bit lower. Humans like to have a low color temperature around them. That's why we like, especially in the evening, we like a fireplace with a red light, etc. So that came out in 2010 as a product, and there were some rooms, I think, at MIT that were had them on their ceilings. That turned out to be not a very good business proposition, because it was good when the light bulbs cost $100 and you could add $2 to it with this film. But when the light bulb costs $5, there's no money to be made anymore with the quantum dots. And also, you have to engineer the optics just right so that the color is uniform, et cetera, et cetera. Light bulbs come in all sorts of morphologies. And if you have to engineer each different type of light bulb, that is really expensive and time-consuming. So really what you want is to take the quantum dots and put them directly on the diode. The diode gets hot, and that's still a problem that people are trying to solve. How to make the dots compatible with the 150, 200 degrees Celsius diode temperature. And there are companies, for instance, Osram, that are still working on that, because that would be the solution. But an easier solution is to go to displays. So this is when the displays started coming out with LEDs as the back color, based on gallium nitride blue LEDs. And so replacing the white coating, the white light coating on the blue LEDs with red and green dots. So this TV here, this is the first TV that came out with quantum dots as the red and green source of light, has a bar on the bottom. Below that bar, a bunch of blue LEDs. The bar is filled with quantum dots that emit green and red. So some of that blue is downshifted to green and red. And now in the back plane, you have a mixture of blue, green, and red. This is a liquid crystal television. So you have filters that allow just the right colors to go through. This is more energy efficient than the previous technology. This was cadmium selenide based. Sony had that TV for 1 year. I have one in my office. I had one in my office, I have one at home. They were great, they were beautiful, but, well, it's Sony. Nothing, I won't say anything more. Samsung, in the background, saw this, this is really interesting, but we don't want any cadmium in there. So they worked really hard to make indium phosphide quantum dots, which the academics had also tried very hard. But indium phosphide is a much harder material to make than calcyanide because it requires higher temperatures, it's more covalent. The chemistry is just more complicated. And given the funding that we can have in academia and the difficulty of this problem, it really did get solved in academia. It was Samsung, because they have a lot of money and a lot of patience. So they solved that problem, and now all their TVs have indium phosphide quantum dots in them. Another application of downshifting, which was slightly more recent, is the idea of a luminescent solar concentrator. Basically, you embed your particles in a waveguide, or a polymer in this case here. The sun shines on the surface, the sunlight gets absorbed by the quantum dots, re-emitting in the red. That gets wave-guided out to the sides, and you put a solar cell here, or you can use that light out. There are a number of companies that are trying to commercialize this idea. You can have downshifting light, but you can also combine quantum dots with electricity. So in this case here, this is trying to get light out directly from the quantum dots by injecting charges rather than electricity to create that exciton, putting that electron directly in the dot from a circuit. This is an electron transport layer, a hole transport layer. You put a voltage across here, current goes through, and this is basically what we call an OLED. This is how your screens, your iPhone screens, for instance, work with organic molecules, the same idea here. And QD Vision showed this. You can make flexible white light. This is what the display companies are hoping is the next step beyond using quantum dots just for downshifting, but replacing the organic molecules with the quantum dots completely and having that as the source of the light for all three colors. This is electrons in, light out. You can also have light in, electrons out. That's called a solar cell. A lot of groups worked on that area here. We did as well. This is me wearing sunglasses made out of quantum dot solar cells here, slightly transparent, powering a little clock here. There are actually companies that use this idea now to make night vision cameras, because you can make your quantum dots absorb into the infrared, and that can then detect the infrared. And detecting the infrared is very important for many applications, and the cameras are very expensive, and presumably these could be made cheaper. It's still a work in progress, but a lot of progress going on there. Okay. I've come to the end of my talk, but I want to conclude here. So what we've created in this field, which is now a very large field all over the world, is chemically synthesized and engineer functional nanomaterials. So these are particles that have a function to them that you can mix and match. You can make semiconductors, as I showed you. You can make metals, semi-metals, magnetic materials, ferroelectric, oxides, whatever you want. You can probably find a way to do it using this idea of nucleation growth. You might be able to do it at room temperature, but most of the time you end up going to a high temperature because of the need for crystallinity. The morphologies, the multiple shells to do different things. You can make them hollow. You can make spheres, cubes, rod, platelets. Nowadays, there are a lot of people that are actually making them helical, chiral, with a handedness. I think this is really interesting. I'm not quite sure what it's good for, but from a chemistry perspective, it's really cool. It's really cool. And then you can separate out of different helicities. And then you can begin to assemble these things like a periodic table and see whether you can combine properties together in different kinds and create new materials with new properties. So this is a big source of research. Applications, the displays, obviously commercial, widespread. Lighting, not so quite yet because of this issue of putting the dots directly on the diode. The biomedical imaging, Quantum Dot Corporation was bought by Molecular Probes, which was bought by Invitrogen, which was bought by Life Technologies, which was bought by Thermo Fisher. So now it's part of Thermo Fisher, but there are a lot of companies that make quantum dots for biomedical imaging. Light sensing through these sorts of cameras, solar energy through solar concentrators. There's a few companies that are trying to commercialize this. More and more today, people are doing research on how to use these materials for photocatalysis, because that goes back to what Lewis was working on. Lewis was interested in photocatalysis, how to use semiconductors to create hydrogen by absorbing the sunlight and getting that electron to do water splitting. Photocatalysis of all sorts, electronics, because these are little tiny pieces of semiconductors, optics, quantum optics, a lot of possibilities. What did I say here? A nano-world of wonders, and it's still going on. Funding was really crucial here, and this is what I show this slide here because, this is academic funding here. NSF, DOE, ONR, Army, NIH, etc. This is funding for companies. We really couldn't have done this with just academic funding. It needed academic funding, government funding, foundations, and more funding directly from companies that are willing to pay what it actually costs to do research, unlike the NSF. This is my last slide, because I really want to say, the heroes of all this work from the beginning, when I was a student and when Chris and Manoj and David were in my group, are the students that actually do the work. All the students and postdocs. And it's because of their hard work and their creativity that we're able to investigate fundamental science, go to applications, and invent new fields. And research takes a lot of people over the years. I've had about 150 or so people through my lab. That takes a lot of money, a lot of mouths to feed, but it's them, that do the work. They're the real heroes. And finally, my last thing is MIT is a great place. I started at MIT in 1990. I've never left. I had the opportunity to leave a number of times. I always stayed here because it's got this environment that values fundamental science, where we can really do basic physics and chemistry, but also surrounded by engineers who care about application, and they keep us keep us in check, so we don't go out and think we're inventing things that are going to change the world when really it's completely impractical. So it's a wonderful place, lots of energetic undergraduates and graduate students, and I couldn't have done this any other place, I think. Thank you. So I really didn't leave time for questions, did I?
Yes, you did leave us time for questions because, what is time?
It's all relative.
Wonderful talk, Moungi, and a wonderful story. I just want to, so I'm Nurgis Mavalvala, and I'm the Dean of the School of Science, and my job here mostly is to thank Moungi and to thank all of the people who are behind putting this wonderful talk together. We do have time for questions. I will save mine for the end, so let me start with taking questions from all of you. If there are questions, there are mics at the two ends here because we have a number of people online as well, so we want to make sure your question is heard. Alternatively, if it's too hard to get to the mic, shout your question and we'll ask Moungi to repeat it. That's another way to handle this. So, okay. Everyone is awestruck. So let me start with my question then. So I told the story, your story of the discovery of quantum dots to my kids. And my little one had a question that I couldn't answer. There were many I couldn't, but he asked me a little. He said, why is it called a dot?
Oh, okay.
As opposed to, as I said, well, it's really small. It's only nanometers. It's smaller than your eye can see. He said, well, that would be a point.
It's a great question. So the term quantum dot was invented by someone that I don't remember his name, Mark. Maybe somebody in the audience remember his name, from the 1990s, physicist. It comes from the progression of a quantum well, which is a two-dimensional material, to a zero-dimensional stuff. And what's zero-dimensional when you look at writing? It's the dot.
I see.
So
I
he
would call
called it
that
a
a delta function, but okay, as a physicist. Wonderful. Are there other questions for Moungi? How often do we get to hear such a story? One other thing that I'm really reminded of from your story, Moungi, is how long it takes to sort of go from ideas to things being built, and to say, for a theorist, you're pretty practical.
In French, it's called un point quantique. It's a point. It's a quantum point.
Okay,
okay,
wonderful. I will return that back to my kids. So thank you. So look, if there are no other questions, let me close us out with a few acknowledgments and thank yous. So first of all, a message. And on the morning of when Moungi's prize was announced at a press conference, he said something that has really stuck with me. He said, "You got to keep trying and doing something that's interesting to you. And more importantly, he said, you have to have the confidence that if it's interesting to you, it's kind of worth doing, even if it's only interesting to just you." That's what you said. I've never had that come to say, it's only interesting to just me. So my message for everybody is take that with you. Even if it's only interesting to just you, keep at it. Good things will come out, maybe even a little round golden thing. So, okay, and then in addition to thanking you, Moungi, for being here, I want to thank the MIT chemistry department, in particular department head Troy Van Voorhis, and department headquarters staff, many of you who are standing there, Danielle Doherty and Corey Lefebvre, and the MIT Alumni Association for making this afternoon possible. So thank you all for being here, for everybody online, and enjoy the rest of your day. So thank you, Moungi.